I want to especially welcome you to the practicals. Okay? This is the first practical. I won't lie to you, what we're about to do now is practical, but it's the same thing you would do if you're writing thesis. It's the same thing I do when I'm writing a journal article. It's like the whole thing, that one thing I know about this course is that it is a course where what you are learning is feeding into your job. So it's not like you are learning something, then you go and, no, the practical, everything is feeding into your job. So if you know the thing, you can do your job. You can do a consultancy, you can publish a paper, you can publish a thesis. So by now, the person would have collected practical data. He has organized the data very nicely, okay? And we are going to use that. I hope I can remember the data set that I used. We have this data set. This data set is made up of 5 DMUs using one normalized output being produced with the usage of 2 inputs. The inputs are X1 and X2. We'll be dealing with this data. For now, let's go to the slides and look at some few things about the software. There are several softwares you can use for R, for DEA. The major one we are going to be using is the R and the R Studio. The R Studio is simply the interface of the R. And there are major packages you use in this R Studio here. Frontier efficiency analysis in R, then benchmarking, then DEAR. These are very popular, but there are other software, new softwares that can do some incredible things. In fact, for the R Studio, you can manipulate them a lot. But these other ones have already been manipulated, so it becomes a click, 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 not programming. The most powerful is MaxDA. EMS is quite long, efficiency management system. LINDEP, Lindo, Ringo, they are more used for linear programming estimations. PIMDA is very good. Okay? It's a bit cheaper as well. DA Frontier is becoming a bit extinct. But you got to know at least 3 of these software so that you can synchronize the results. When I say synchronize the results, sometimes you can program, you're having challenges, but you don't really know what the problem is. So when you have another one, then you can go and do that, not command-driven, but menu-driven, and then you can use that menu-driven one to verify the results you have. So get to know the R Studio or the R1, and then know the MaxDEA, and then the PIMDEA. The MaxDEA and the PIMDEA, you have to buy it. The MaxDEA is very expensive. The PIMDEA is not expensive. Okay. Now, why do we use R? Because R is a very, very powerful package. It can handle very, very powerful software with a lot of packages, and it can handle matrices. And so, you see, you can have a large data set. You can combine it into a matrix. If you can remember regression, you have the independent variables plenty, but you can put all of that into one matrix. And R is good in dealing with that. So because behind the scene, we are using matrix rules, it's very important to know a few things about matrix and vectors. Very 2 simple, important points. One of them is concatenation. Okay, concatenation of matrices is done in such a way that you can split matrices. Sorry, you can combine matrices to create a larger one. So you can have a matrix A and a matrix B, and then you can concatenate the 2, combine the 2 to create a matrix C. We shall do an example of that. Let's go here. So here we have 2 matrices. They are all column matrices. They have the same number of rows, the same number, and what we are going to do is that we are going to combine them, concatenate them into a larger matrix. So let's go to the R. You see this matrix called B. This B is a column matrix. That is why you see the letter C here, okay? Column matrix. And you are going to have, sorry, it's not a column matrix. It's just a combined matrix, and then we are going to separate them. You have 2, 4, 3, 1, and 7. Okay. The first thing you want to do is to copy this one and take it to your R. This 2, 4, 3, 1, and 7 is a matrix, but you want to split them. You want to indicate the number of rows is 3. So if the number of rows is 3 and the number of columns is 2, It means that if we are going to have two columns, then the first one here will be column 1. Because if you look at it, there are two columns. So the first 3 will be column 1, then the next 3 will be column 2. So you can have, the way I'm showing my hands, you can have 2 up, 4 in the middle, 3 down. Okay, then the next right, which is the second column, will be 1 up, 5 in the middle, 7 down. That is a column. And again, you check, because there are 3 rows. So you can see that the 2 and the 1 will be 1 row. The 4 and the 5 will be another row. And then the 3 and the 7 will be another row. So when you run this and indicate the commands here, you're going to get something like what we're about to show you. So let's go up here and you see. So this is the matrix. I'm going to run that. And when you run that, it will automatically be split. How do you know it's split? Once you run this matrix, when I say run, I mean you look at the top, you run. Just highlight the B and run again. And you can see that it has split them nicely into the 3 rows and 2 columns. So that is a matrix. Now, this is a matrix. A matrix will have vectors in it. Okay, so a 1-column matrix is a vector. But this is not a 1-column matrix. This is what? A 2-column matrix. Sorry. Yeah, this is a 2-column matrix. Okay. You have column 1, column 2. So this is not a vector. This is a matrix. Let's take another matrix. If you look at matrix B, that one, the rows are 3, the columns are 1. So how will you arrange it? It will be 7, 4, 2 coming down. 7 in the top, 4 in the middle, 2 at the down. That is top, middle, down, top, middle, down. So let's run this second command, and that will give you top, middle, down. If you want to see how it is, you run it, and then you see this top, middle, down. What about the next one? The next one is a column binding. So what you are going to do is that you're going to put column B, matrix B, and matrix C together. It's a very, very simple thing. Okay? Just put it together, arrange them together. It's a column. Okay? So it means that if this is C, this is B, the next one should be on the right of it. Okay? So let's put that there. That's it. So you can see that we've combined the columns. Sorry? Yeah, you should be running. You should, if you have the commands, so you copy the commands from the PDF, put it in the Excel, you run. Or put it in the PDF, okay, you run. You should be getting what I'm getting. But have you copied them? If you have copied them, just ensure in the R that they are well copied. If I didn't close the bracket, remember there's a close bracket. You can control power. No, if you want it to come, you highlight only the B and run the yellow. Good. Highlight only B, run the yellow. That's when the thing will show down there. So that's when you show results. So you show results by highlighting the very left-hand side of the equation. So the other one you have done for C, you do the same thing. You highlight it and you show. You highlight and you show. Let's look at D. There's another matrix. It's a 1 row, 2 column. So it's going to be left and right. 1 row, 2 column. When you run that and you show, showing means that you highlight the D and then run that. You highlight the D, then you run that. Now we can row bind B and D. We can row bind B and D. So you put all of them on the same row. Now if you look at B, it is 2, 1, 4, 2, 4, 5, 3, 7. Okay. And if you look at D, it is 6, 1, 2. So if you're going to now row bind them, you're going to just add the 6, 2 to the 3, 7 in the same format. So let's see that. You can see that it is showing that the 6, 2 is continuing the 3, 7. That's it. There's some data These data are already pre-installed into R. And you can look at this data yourself. So sometimes you call for the data. It came along with the R, and then you can bring them along. One of these data is plant growth. I can show you how plant growth looks like. This is how plant growth looks like. It's a very simple. I'm not interested in all of this, so focus here. What I'm interested is the required benchmarking. So please, you must have installed benchmarking. How do you know you have installed it? Go to the packages section. And when I say packages section, okay, this is what I mean by packages. Go to packages here. Click on packages. And then when you click on packages, you see install. You see install. Click on install. Well, don't click on install. Before you click on install, go through the list alphabetically. I'm scrolling down. I'm looking for benchmarking. 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 You can see that in my list, I have benchmarking here. Okay. In my list, I have benchmarking. This is benchmarking. Do you have benchmarking? I have already installed a package, but to install it, click on packages, choose install, a pop-up will show. And then in the list, start typing benchmarking. The internet is good, it will start popping. It will start popping. Now that you have installed a package, you're going to go ahead and run the package. And how do you run the package? To run the package, you need to type it into the command window. So if it's not in the command window, type it like I have done here. And then while the cursor is blinking at that number 8 here, you will run. You will invoke the package. So you type require into bracket benchmarking. And when you are typing the benchmarking, you see that it will start popping. So type require into bracket benchmarking. Once you have done that, by the way, when you do that, it will show down there in the console, down here, which means that it has been loaded. Now we are ready to start our analysis. To start our analysis, go back and install, copy the data set. So this is a data set. Copy the one I have highlighted in yellow. So you do Control A to highlight, Control C to copy. You come to your R Studio now. And in this R Studio, you click on this command number 11 to bring the data from Excel to R. What you're doing is that you are importing the data from Excel into R. But when it comes to R, you don't paste, as we know. I call the name of the data Farm1. Yeah. No, just the one I highlighted. Yeah. So I just did that. And to see the results, you can run the next command. And you can see that the data is nicely in the Excel, the R at the bottom. All right, so now that you can see the results, the next thing is to follow this information here. What we are going to just copy and paste, like I said already. This information, what it does is that it converts the column DMU names into row names, and then it will label the data set as farm. So you copy this command and paste it. which I have done already. So I'm just going to show you. So this very command here, this command, what it's doing is that it is a FAM1 data, but it's removing the first column. So that's why you see comma -1. It's removing the first column. And by the way, the first column is the name of the DMU. So if you look at the first column is DMU and then the names under it. We are removing that column and giving it to the one on the left, which is 1, 2, 3, 4. So we are going to give the 1, 2, 3, 4 the names of the DMU. So let's run this first column. When you run the first column and then you show this result, you will see that the DMU has been removed. Okay. You see that the DMU has been removed. Now we insert it back by replacing the number 1, 2, 3, 4 on the far left column. We are going to insert that with the names of the DMUs that were removed. So we run this second command, command number 22, with the row names. Okay. And once you do the row names, go back and run the FAM. Okay. Because if you look at the row names, what you are saying is that now bring back the DMU names into the FAM1 and call it FAM. Now let's run the FAM again. You see that the FAM has replaced all of that information that you see there. So you just do that. Let me know. All right, let's move on. So now I can show the names of the data. All of them are not necessary. What is necessary is what we're about to do, combining the elements into input. That's what you should. So now, if you look at this command, it's X bind, this one. Okay, copy and paste. Copy the Y, which is the C bind. Copy and paste that one. So run this command. You see, what we are doing is that the X1 and the X2, we are putting it together and labeling it as one matrix, input matrix, and calling it X. X1 and X2. We are combining the two together into one matrix called X. And now when I show the X, you can see that it's giving me both the X1 and the X2. What you got to do is to just copy paste before I even get there. That's the whole point. You don't even need to run, just copy paste. By the time I get there, you've already done it. Normally, ideally, these copyings and things has to be done before we even meet. Okay, then we do the Y. The Y is also a C bind. That one, every Y, if the Y's were 100, you put all of them together and call it capital Y or small y. And when you show the results, you see that they are all 1, 1, 1, 1, 1, 1. Remember, it's a column bind. Each one of them is a column bind. I'm not going to do the W, which are for the input prices. That is needed only when you're doing cost efficiency. That's for later time. No, don't do it. Yeah, move to X1, that's it. Now, this X1 and X2 that we're about to do, it is only because we want to draw the curve. That's it. If we were not going to draw the curve, we wouldn't have done. So let's run these two commands. I've just run the two of them. So we are going to rename the X1 as X1 and rename the X2 as X2 for purposes of drawing. Now we can plot it since we have renamed it as X1 and X2. And in the plot, before the plot, there are some few things that I've given in the slides. For example, before the plot, you must have invoked benchmarking, which we have done already above. So there's no need to do that invoking of the benchmarking. So that part is not a problem. The next one is we are going to draw a graph. So there are some things you should know in R. COL means color. And again, all of these are in your slides. COL is color. LWD is the line width, the width of the line, or how thick it is. DIM is the dimensions. PCH is the symbol type. Okay? There are several symbols. 0 means you want the symbols to be box. 2 means you want the symbols to be triangle. 3 means you want the symbols to be plus. So the data point, okay? You can make the data point 4. When you choose 4, it means you want the data points to be times. I'll show you an example very soon. Then 15 is when you want it to be filled box. 8 is when you want it to be a star. The 6 is the size of the text symbol, the size of the text symbol. Okay. And then the LTY is a type of line, whether it's a zigzag line, a deep line, double zigzag line, and all of that. And then the POS is a position of the text. So when you write a text, you want the text to be on top of the point, or on the left of the point, or below the point, or on the right of the point. Those are the numbers here, okay, that will showcase each one of them that you are looking at. So with that in mind, let's go to the plot. Go to the plot. The first plot I have here, you can use any name. It's not. Okay. For example, here, I call it DEA isocont. You can call it anything. Okay. So DEA isocont. So it starts with plot X1 and X2. The color here, I've chosen purple. But in your slide, yours is blue, isn't it? Yeah, no problem. I've changed the blue to purple. The line weight is 5. I've changed mine to be 2. The PCH is a type of the symbol. Okay? And here I have 8. You can change the symbol to 15. 15 will be a filled box. Now you guys are having, I think, 8. I want to change this 8 to 15 so that you see how it will be different from mine. The sex is the position, the text, the size of the text or symbol. So if it is 1, you see the size. If it's 2, it's getting really deep. And then the main means that you want to know the title of the plot. Let's do that and see. I'm going to do that here. And then on the right, you can see how mine is looking at. See, that's a scatter plot of the data for mine. You should run yours and you should be able to get a plot. If I had changed the 15 to 8, it will be stars. Okay, let me just do that, 8. Okay. It will be stars, as you can see now. The purple is what I use. If I don't want purple and I want yellow, watch it. The moment I choose yellow, watch it, you see that they will all tend to yellow. If I don't want yellow and I want green, well, green is there. It's going to be used pretty soon. If I want green, you can see that straight away you get a green symbol. Whatever you want, you can get that as well. All right. So there are several things. You can explore many of these. And then you can find. There's another one where I've changed and increased some of the numbers. Like that. You can have several of these things. In fact, you can even do it in such a way that some of them will have, each one of them can have different colors. Yeah. So look at what I've just done here. I've done it in such a way that each one of them has what? A different color. So these commands are all there for you to explore. But you know, these are DMUs, right? Yeah, these are DMUs. So that is how you got to approach it. Now we are ready to draw the isocont. And how do you do that? This is the most important command in the DEA. We're going to draw the isocant. This is what you have in yours. So copy this DEA plot. You see, the first one was a plot. It's like a scatter plot. But the second one is a DEA plot. Oh, I've done this already. No, I haven't done. Let's do that. DEA plot. So watch what I'm doing here. I've just did the DEA plot. And you can see that it has drawn the isocant, more or less. It's drawn the isocant. I still have my colors changed. I still have it. But now we don't even know which one is DMU1, DMU2, and all of that. So that's the next important thing we are going to do. We're going to draw the radial lines. We're going to label the DMU. Now remember, this is only possible in the two variable case. One input, one output, or two inputs, or two outputs. Have we done this? Okay, good. Now let's add a text. If you want to add a text, this command, this is a command you add to it. So let's add a text. So we are going to look at each DMU and insert the text. I'm going to do the text here. There you go. You can see that the text is on top or above each of the symbols. If it is small, I can make it big. Okay. The position is that. If it is small, I can make it big. So this CX is 0.6. I can even make it like 2 and run it again. Watch it. See, now it's too big. So you got to go back and then let's make it like 1. Okay. So it inserts upon the other. So if you want it to change, you got to go back and run this last one again. And then you run the DA plot like that. Then you run this. Yeah. No, if you are running in this case, just click the cursor. Just click anywhere. You don't need to highlight anything. Just click anywhere in that line, in that horizontal line, and just run it. So as you can see, we have labeled the DMU. I lost it. Isocant. Isaac, do you have an isocant? Okay. So we go to the next thing. So you can see that we have the isocant, and then we have the text. In case you haven't done the text, you go to this command and do the text too. So this command, you do the text. The text means that you want the text. Then the for that will draw the radial lines. So do that one too. Draw the radial lines. Everything. So I'm going to add the for. And now you can see that I've drawn my radial lines. I made the colors black. So now this whole thing that we could have done in Excel, you can also do it right here. I got to know that a lot of programming has to go into place, Abby, to be able to execute that. Let me know when you've done the radial line. When you run the radial lines, you are going to get to this bit program. You can export to this one, actually. The two of you done with this. You export as what? No, don't do it. Normally, when you need it to use for other things, then fine. But other than that, there's no need. As long as you've done up to this level, you let me know. Done? All right. So this is just a graphical interpretation. Now we need to estimate the scores, which is the most important. Remember, in real market systems, you will not do this whole graphical. Because in real market system, you have input 1, input 2, input 3, input 4, input 5, output 1, output 2. So you can't do a 2D graph. This is just a way to demonstrate something. And we are ready to estimate the efficiency scores, and you need this command to do it, which is in yours. So you're going to run the technical efficiency scores under CRS. Then you run the technical efficiency scores under VRS. We have that. Just go and then show those results. I will show mine here. I just did the running. It has been done. And so you can do a summary to see the results. A summary of the first one. Okay. This first one will just give you a summary of your results. When you do up to the summary of your results, let me know. You get it? So technical efficiency, CRS, the returns to scale, RTS, is the constant returns. Okay. Then the VRS, the returns to scale, is that VRS simply means that size matters in the industry. CRS means that size doesn't matter. All of them have the same size. They are all operating at the same optimal scale size. Okay. And one interesting thing about CRS and VRS is this, and you should know this, is the fact that CRS, or constant returns to scale, is for industries that are usually robotic or manufacturing. Because they are not using a lot of labor who behave strangely. They are using capital, most capital-intensive business. Then VRS, which says that size can differ. So size can play a role in determining the efficiency. It is for service industry in particular, because you can have management behaving differently or being paid differently from lower level staff because of the intellectual acumen or because of the experience, the skills, the knowledge, the wisdom that they bring to bear. So that makes it different. Also, industries where the size of the company differ. Industries where the size of the company differs, such industries are said to have VRS. For example, you can take a banking industry, and the biggest bank, when I say biggest, bigger by total assets, the biggest bank is huge, billions. Then the smallest bank is not huge, millions. So you can see that there's a lot of disparity. So normally when you are generating the descriptive statistics for the variable, you will know the range. When you look at the maximum value and the minimum value, the maximum and the minimum value will tell you that there is a big range between the bigger guy and the smaller guy. When the range is big, that will give you the clue that then it appears that VRS is operating, because VRS means that there is a lot of variability. However, let me give you another clue to see that the industry can exhibit VRS. That is when you have the mean and the standard deviation is bigger than the mean. So let's say you calculate the mean of maybe a particular variable. So let's say you have the labor, the number of workers for the firms in the industry. And then you calculate it, then the average number of workers is 20. That's the mean. Then you find that the standard deviation is 28. The fact that the standard deviation is bigger than the mean shows that there is a lot of disparity between the companies in terms of size. In other words, some are too big and some are too small. Somebody would say that that's how it is in most African countries. Some become too rich and some become too poor. Like, after all, you should be rich and poor, but too rich, too poor. And in such a case, you cannot run it using constant returns to scale. The evidence is there for you to use variable returns to scale. But you see, what these experts have done is that they have also created a statistical testing that can be used to tell whether the industry is truly VRS or truly CRS. And that is called the non-parametric test of retention scale. Normally, when I'm supervising you, it's one of the first things you do when you are about to run any analysis. You run that first. You verify that size is not a big issue. Because if size is a big issue, you have to use VRS. If size is not a big issue, you have to use CRS. Okay, so let's look at the CRS result. Now, remember that these are just 5 firms. So when you run the CRS result and you run the VRS result, they'll give you the same thing. Yeah, they'll give you the same thing. Oh, do you see that there's another thing called slacks equals to T? You see that? The slacks is equal to T. Okay. So you can see that the slack is true, which means that you're telling it that if there are slacks, okay, we would like to see it. In other words, allow us to calculate the slacks. So you do that, and then you look at a summary. The summary says that summary of efficiencies, okay, constant retention scale technology is being used. This is input orientation. That is also being used. And you can see that the number of firms mean efficiency. So how many firms are efficient? The summary tells you. So this is where you don't have graph, okay, and you have plenty data sets. Now the summary is talking to you. How many firms are efficient? When I say how many firms are efficient, how many firms have an efficiency score equal to 1? Equal to 1. The summary has given you. Look at the summary result. Unless you've not run the summary result. The summary result says that it tells you there. It says, read it, read what it says. So what does that mean? You've mixed it. It says the number of efficiencies, the number of firms with efficiency score of 1. That is why it has double equality. Double equality here means strictly efficient. That is fully efficient. So that efficiency is fully efficient that is looking at. Number of firms with full efficiency of 1, not weak efficient, but full efficient. And there are 2 out of the 5 firms. That's what he's saying. There are 2 out of the 5 firms. And you know that that was true because if you look at DMU2 and DMU5 in our result, graphically, they were. I remember, like I said, you will not get that in real situation. So in real situation, you will now know how many firms are fully efficient, which means that these are the only firms that can become peers and role models. Take note. They are the only ones who can become peers and role models. Okay. Then it also tells you the mean efficiency. What is the mean efficiency here? Yes. So you will notice that this industry, this small industry of 5 firms, has a mean efficiency score of 81%. Question is that good or bad? Well, we don't have any benchmark to compare whether that is good or bad. So actually, the good thing is that you're able to get a bit of the efficiency. Let's go to the range. So it gives you a range of those that are efficiency of between 0.5 and 0.6. And it says the number of them are 1, making 20%. Those that have efficiency of 0.6 and 0.7, there's nobody with an efficiency range of like that. So it is 0. Then it gives you those that with 70 to 80%. They are also only 1, and then the rest. It gives you the mean, the median, the third quartile, and the maximum and minimum value. That's a summary. Now let's get individual efficiency scores by running the command TECRS. So when you do TECRS, you get this result, which is for each one. But these results I don't like. So I like the one that is printed. Okay. So let me show you the one that is printed. So when you go here, the last but one, in fact, the last but one bullet, and then I like the last bullet here, the one that shows you this, the up to 2 decimal places. I think up to 3 decimal places is good. So let's run the one up to 3 decimal places. So I'm going to do for the constant returns and also for the variable returns. And you can even combine all. So in this case, my command number 56 combines all so that you have it all in one table. Let me see whether you have that here. You guys don't have, but you can run it. So look at the last one here. You see the last command here is round the data frame. Let me see. Round the data frame, and then the technical efficiency score. Watch the way he's written the technical efficiency score. We wrote TECRS, which is $EFF. So we are picking the results from $EFF. And then the variable returns one, I add that as well. Okay. And then I use 2 decimal places here, but I wanted to change the 2 decimal to 3 decimal places. We are going to add more to the data frame. Remember, this is data frame. Emily, do you have a question?
Doc, I was just trying to say that the TE, if they run it like that, it's going to give an error. It has to be TECRS $EFF. I don't know if you're getting me. The round data frame.
The round data frame,
Yeah, if you run it just as it is the TE, it comes as an error that the object TE not found.
Oh, okay, yeah, you're right, because you're very right, because it's supposed to be TECRS, just like the second one is correct. So it's true. So you can see that this one is supposed to use this name. You see, this one is TEVRS. And that is the same thing you are using for that. So this one is supposed to be TECRS. So when you are running, edit it. Okay, so I have mine here, and I can see that even though I did that, I have run the correct one here. It's TECRS. So let's run that and see the results down there. TE, you bring the TE here. Check that. So you have to add this and you upload. Not everywhere you have that dot, just double check the results. That dot means that some things are deleted. Okay, so at the bottom, you can see the results are shown. Okay. Let me tell you what you will get. You are going to get something like that. You're going to get something like what I am showing you here, where you have the TECRS, TEVRS. Okay. I can give you any name for that. But there's a difference between the two. Take note. The TECRS is what we call the overall technical efficiency. Take note. It is the one called the overall technical efficiency. Then the TEVRS is called pure technical efficiency. Pure technical efficiency. What is the difference? The first one, which is the overall technical efficiency, it is infected with size. It incorporates elements of size. But the pure deals with pure technical efficiency. I'll give you an example, practical example. Suppose you determine the technical efficiency of a firm. You will attribute that to whose efficiency? If you calculate, whose efficiency is that? The managers. So that technical efficiency is also called managerial efficiency. But when you say managers too, what do you mean? You are talking about the manager's knowledge, experience, technical know-how. And what if the efficiency is bad? Then it means you're going to attribute it to management, Abby. Now, normally, when it is bad, they don't like it, isn't it? They will tell you that it's not me. And so what is it? Sometimes, truly, it's not them because it is something they don't have control over. We said this thing before. And that thing they don't have control over is what is punishing them. Let me give you an example. Let's say that you go to school, the students are so bad, everybody's failing. Everybody's failing. And you might think that it's the teachers who are not good. But the teachers are good. When you look at it, there is something, the size of the student body is too large. And because the size of the student body, or there are some things that are not at the disposal of the student. Maybe there's no library to study. So this size element, these factors that management don't control, the teachers don't have control over. That's what is affected. So when you tell them that this managerial efficiency is as a result of the managers not doing good, they don't get it. They don't think that that is their fault. So they will tell you that give us our pure technical efficiency. So the pure technical efficiency is technical efficiency attributable purely to management performance. Exactly management performance. But the other one is management performance all right vis-a-vis or under the circumstance of the skill or the structure of the company. You got to know that. The overall efficiency includes something we call scale efficiency. The scale is size. Scale is size. In this very example, they are the same. There is no big difference between the overall technical efficiency and pure technical efficiency. Don't forget. There is no difference between them. So take note, overall technical efficiency is not the same as pure technical efficiency. All right. So remember that pure technical efficiency is only attributable to management performance. Now that you've gotten your efficiency results, you can generate the density, the distribution of the efficiency. And when you look at the slides, you will see it. So this is a distribution of efficiency. You use this to show the distribution. You're going to do for the VRS. In fact, you can do for both VRS and CRS and then check the result. I've forgotten, but then you can do for both. Anyway, so this is the first one. You can see the distribution, the density of efficiency. You can see that the thing keeps rising until it gets to 1, and it truncates at 1. It truncates at 1. Actually, you can do for both. You can do the density plot for both. Just like that. If you look here, we were talking about the density. You can run this and then show the plotting density, the density of the efficiency score. Then we can also show most of these things regarding the density. We can show the PS. So when you look at this result here, you have the PS. Okay, you have the PS for DME1. You can see that the peer used DME2 as its peer. Remember, DME2 is efficient and 5 is also efficient. Okay. So use DME2 as efficient. That was the only one. DME2 used itself as an efficient. There was no second one. DME3 and 4, it used 2 and 5 as its peers. Okay. And you will only be used as a peer if you are an efficient firm without slacks. Okay. So that is it. Then this next command talks about the number of peers. Okay. So how many times, which firms were used as peers? DME2 and 5. Remember, they were efficient. DME2 was used twice as a peer. DME2 was used 4 times as a peer, and DME5 was used 3 times as a peer. So, and you can ask the question, which are the firms that firm 1 and 5 use as peer? This question will give you that. Which are the firms that firm 1 used? 1 and 5 is peers for. So 1 and 5, okay, they are peers for which firm? 5 was a peer for firm 3, firm 4, and then for itself. And this is the most important one, the slacks. And you can calculate the slacks here. You can see that there is no slacks in this one here. You can also see that there is, you can calculate the scale efficiency, which is a S. I already told you that the overall technical efficiency divided by the pure technical efficiency equals a scale efficiency. Just note that down. Note that down. The overall TE divided by the pure TE will give you the SE, which is a scale efficiency. It's the same as saying that the constant returns technical efficiency, the CRS technical efficiency, or what we call TE CRS, divided by TE VRS equals SE. Take note. So anytime you have something and you have to calculate the scale efficiency, just go and look for the technical efficiency CRS, divide it by the technical efficiency VRS, and that will give you the scale. And in fact, that's what I just did here. Let's run the results and see. So look at this final result. This final result is key. And this is a sort of result I would be giving. Let me put it in a proper data frame like this. Don't worry, you'll get it very soon. By the way, all of these things, I've just done all of them and I've just put it together. So you can see that the first part is the data set. You see that? If you look at it, the first part that you guys are seeing is a data set. So when you go here, you will see that the data set is here. This is it. So that part is a done deal. The second one is the technical efficiency under VRS. That's this, under VRS. And this is, the next one is under CRS, Then the technical efficiency under VRS. Then the scale efficiency is the next one. Remember the scale efficiency, we got it by dividing the CRS1 by the VRS1. So if you take the first one, you have 0.5 divided by 0.5. That's why the scale efficiency is 1, because for this very data, the CRS score is the same as the VRS score. The next one is the slacks. Remember, even at the graph, remember that when you trace the DMU 1, it will hit the free disposable section. Okay, so it means that here the DMU 1 had a slack. So that's what you can see here. So under slack, you can see that he has written true for DMU 1. Okay. True means that it has a slack. And then it shows the value of the slack, as you can see here. It's 0.5. If you can remember, it was 0.5 units to get to the 2. You remember that then? Yes, you can see it here. If you check even this one, I'm just going back in the graph. Look at it. So if you look at this one here, you can see that when you trace DMU1, it doesn't hit the frontier at DMU2. It hit it on the free disposable section, which means it's created slacks. And to get to the slacks, you have to move 0.5 down to 2. So DMU1 is not just technically inefficient, if you look at it. Well, it's not on the frontier, so obviously it's not technically efficient. It's technically inefficient. But apart from that, if it wants to achieve efficiency, it will hit the free disposable section. So it is also mixed inefficient. Anytime a firm is mixed inefficient, that firm has slacks. Keep that. Anytime a firm is mixed inefficient, it also has slacks. And DMU1 was the only one that has that. If you check DMU3 and 4, they are inefficient technically. But then when you trace them to the frontier, they don't hit the free disposability section. So if you check this guy, when you trace it, when you trace this guy, they don't hit the free disposability section. They hit a section which is feasible and is efficient. So if you look at it, they hit between 2 and 5. And between 2 and 5, everything between 2 and 5, there's no slacks there. So DMU4, there's no slacks. So even though these two are inefficient, they don't generate any slacks. And you can see that they are all false. There's no slacks that they are generating there. All right. Let me just go to the last bit and then we can now look at the entire data set. So the last bit here is this, target. I wonder if you guys have it. But please, I'm going to give you the formula because I doubt if you guys have it. Let me see. So I've spoken about all of these PS, and everything. I draw, I show. I've spoken about the slacks as well. I draw, I show. Okay, now lambdas. And then the lambdas will eventually lead to targets. Let me see whether you have that. No. Okay, so it's true. So please watch the formula for the target. You calculate it here, but then in the R, I left it. Oh, you have it here. Yeah, you have it. Let me just show you. So I'm going to show this command. This command computes target. What is the definition of efficiency? Keep that in mind. It's a target over the actual. Write it down. It's a target over the actual. The actual is what you have in the data. So if the actual in the data is 4 and the target is 2.5, then it will be 2.5 divided by 4. That will give you the efficiency score for input oriented. But for output oriented, the target will be more and the actual will be less. It will be 4 over 2.5. That's why the score is normally above 1 for output oriented. Now, so we are going to calculate the target. How do you do that? Watch this. Okay. And what I want you to note is to know the formula for the target calculation. So please write it down. Write it down in the R. When you go home, you run that. TRG to refer to target. TRG is just to refer to the target. That is equal to bracket. And inside the bracket, you're going to have the following. You have TECRS $EFF. TECRS $EFF times X. By the way, the TE, just write, don't worry. I mean, you can see it here. Okay. TECRS $EFF times X minus bracket SL. SL is a slash. Bracket SL $SX. X SL silicon lithium $silicon xylophone. And close the bracket and you close the bracket again. This will compute the target. So look at it and let's see what it means. Technically, what it means is this. It means that the target, it means that the target is equal to the efficiency score. Let's say it's theta. multiplying the input, if it is input orientation, minus any possible slacks. That's it. Minus any possible slacks. Guys, do you remember I told you, suppose there was no slacks. Do you remember I told you that the efficiency score, the theta, if you want theta right now, theta will be equal to what? If you want theta right now, suppose the slacks are 0, S is 0, theta will be what?
Yeah. Doc.
Yeah.
Doc, I come in.
Yeah, come in.
Okay, Doc, it will be target over the actual.
It will be the target here divided by the actual. I told you that if S is 0, if S is 0 and you want target, T, you want theta. Okay, so that is theta. I mean, when your mind is closed, it's closed. That one, when your mind is closed, and there's a lot of, jollof in the mind. Kebab in particular is in the mind. When there's kebab in the mind, there is nothing that can. So this one, so if I said I'm looking for target is just cross multiplying. That's what gave us the power. But you always have to subtract slacks. If the slacks is 0, then no problem. If the slacks is not 0, no problem. You will calculate target a lot. Okay, I just wanted to know that's how you calculate target. All right. So how do we get target of any particular? Let's run this and see. In the event that the slack is not 0, multiply the theta, which is efficiency score, by the actual, and then go to the slack and remove the slacks from it. Okay. So let's do that here. I'm going to do that here. I just did that. Now let's see the result. It's going to be the last column. That's it. That's going to be the last column there. So watch it very carefully. Let's go to those that are efficient first. In this data set, remember the efficient ones are DMU 2 and 5. Remember? You remember? Okay. DMU 2 and 5. Look at DMU 2. The input, the target. The target, remember the inputs are 2. So X1 target, S2 target. S1 target is what? 1. S2 target is what? Is 2. Now, let's compare that with the actual values. The actual values. When I say actual values in the data set, look at DME2. The actual is what? Actual X1 is what? No, look at it. X1. That's what I'm saying. DME2 is 1. It's the same as the one you have here. It's the same one. And then for the X2 is what? That's the same thing here. And we know that when you are efficient, fully efficient, your actual and your target are what? Are the same. That's what you see there. And for DMU5, remember that one too. This is DMU5. The actual for X1 is what? 3. And then the actual for X2 is what? Let's check here. These are the targets. You get the same thing. Okay. So that helps you to know how the target was calculated. But now check this. DME2. In fact, let's look at even DME1. DME1. DME1, the actual is what? The actual X1 is what? And then the actual X2 is what? Okay, let's go to the actual S1. Instead of 2 is what? 1. So it means that it has to bring the 2 down to 1. And then the actual S2 is what? But it was 5. So it has to bring the 5 down to 2. So there are slacks. And those slacks have caused the target to be lower. Okay, so you got to bring those down before you can be efficient. That is why on the graph here, you can check the graph here. We brought it down. Okay, watch it. We brought this one down here. And then if I were to go by that, but more importantly, we brought it to this section. And then after bringing it to this section, we went down here. So if you look at it, X1, look at X1. X1 was 2, but it's supposed to be 1. And you can see that here. This is X1. Okay. At it stands at the top, there is 2. So it's supposed to come down to what? 1. That's it. And then X2 was 5. And you can see it here. X2 is 5. It has to also come down to 1, 2, 3 steps. That is to 2. And that is what you are seeing here as a target. So in short, you are able to calculate the target for each DMU using this formula. It's very important. Learn how to use this formula to get the target. Now, if you check the formula carefully, the only thing that I'm using here is theta and the actual, the efficiency score and the actual. But if there are slacks, you take care of the slacks as well. Now let's check the efficiency score for DMU 1. The efficiency score for DMU 1 was 50%. Do you remember? Well, in case you don't know, it's here. Okay. That's the efficiency score for DMU 1. It's 50%. So let's take the 50% and multiply that by the input, X1. X1 input is here. This is the X1 input. This one. So if you multiply 0.5 by the X1 input, which is 2, what do you get? 0.5 times 2. You get 1. And that 1 is what you have here. Okay. That 1 is what you have here as the target. Now let's say the same 0.5 multiplied by 5. Remember, the second input is 5. 0.5 by 5. What do you get? 2.5. Good. But that's not what you got here. Why? Oh, no. Because there's a slack. And you can remember it here. So it got that 2 here. What is 2.5 here? And then you use the slack. You have to take it. So that's why this formula says that let the slacks also be taken out. So when there's a slack, take it out. If the slack was 0, then you don't have anything to take out. That is when the thing is back. So what I mean is I learned how to calculate target, which is a formula I've given you on the screen. There is a second formula for calculating target. It's even more difficult than this one. That is using the lambdas. You see these lambdas here? These lambdas here. You can use this one to calculate the slacks. As for that, it is in the slides. It's in the slides. In the slides. Let me show you one. So this is it. We can go and calculate the target for this guy. Let's try one of them. So I just want you to know about this lambdas first. This is the lambda. The lambdas are the weights. Watch it. It is the weight of the peers for each firm. Is the weight of the peers for each firm. The weight of the peers for each firm. In other words, like the importance you are placing on that firm in helping you to achieve your goal. So watch it. When you type this command, which we have done already, when you type this command here, okay, it will give you the lambda for each. And the lambda is a weight. It give you the lambda of the peer for each firm. Remember, the lambda is the weight of the peers. The weight of the peer. So who is your peer? If your peer is me, then my weight for you. If your peer is me, then my weight for you. If your peer is me, if your role model is me, then my weight for you. That's a lambda. Okay. So let's go to DME3. This is very important. This is the last thing I'm doing for today. If you check DME3, okay, the lambda for DME3 is 0.6665. Sorry, 0.6667. Let's go to the result and see. This is it here. 0.66667. That's it. That's a lambda for DMU3. Remember, we're going to use this to calculate target too. So now, that's a lambda. And for DMU2, and this 0.6663, it was from DMU2. So DMU2 was its peer. How do you know that? But when you go to the graph, you see it. Who are the peers? Where's that? I don't even show the peers thing. But by the way, if you check DMU3, you can see that it has a value. This one shows that it is picking it from DMU2. L2 means that it's taking it from DMU2. L3 means that it's taking it from DMU what? 5. DMU5. Yeah, I'm saying that this is 0.6667. Oh, sorry, L5, sorry. L5. So it is copying from L2. In fact, all of them are copying from L2, DMU2, and DMU5. Now, the lambda coming from DMU2 for DMU3 is 67%. And then the lambda coming from DMU5 for DMU3 is 33%. How do you use this to calculate the target for DMU3? This is how you do it. If you check the target for DMU4, it's also the same thing. It's from DMU2 and it's also from DMU5. This is how you calculate it. You can use this lambda for DMU2 and the lambda for DMU5, these two information, to find the target, also called a benchmark for DMU3. So if I want to know the target for DMU3, there are 2 ways to arrive there. Take note. What are the 2 ways for arriving at the target? I always ask this question. That's why I'm standing here. The 2 ways for finding the target. 1, you have to use the theta, taking into consideration the slack. We just finished that one. Use theta, noting the slacks. Use the theta, but don't forget the slacks. The second one is use the lambdas. Somebody will say, but forget the slacks. You have to still remember the slacks. Yeah. Let's try for DMU3. How do you find the target? The word target simply means take the lambda, multiply it by the variable. So let's look at DMU3. DMU3, the lambdas were 0.6667 and 0.3333. Do you remember? 0.6667 was coming from DMU2. Well, let me just go back, see. The lambdas are 0.6667 and 0.3333. 0.67 was coming from DMU2. 0.333 was coming from DMU5. So what we are going to do, and we are saying that this very inputs for this guy, they are bad. That's why he's inefficient, 83%. They are bad. So how do you get its target? Well, in order to get its target, take this 0.666, which is from DMU2, multiply it by DMU2's input. What are the DMU2's input? The input one was this. So I'm going to take that 0.666 and then multiply it by the one for DMU2. You can't even use himself because he's not even good. So you have to go and take that of DMU2 plus you take the 0.333 multiply by the input of who? DMU5. So you take this 0.333 and then you come to DMU5 here, its input, which is what? 3. So you take the 0.333 and multiply it by the 3. Whatever that you will get will be the input one for DMU3. That's a point that I calculated it. Let me just show you. Whether or not there's diminishing returns, a woman. So that's how I calculate it. I take the lambda, multiply it by the input of DMU2. Then I take the lambda, which is a 0.333, multiply it by the input of DMU5. So this is how I did it. I take the 0.666, multiply it by the 1, which is what I did. Plus, I take the 0.333, multiply it by the, and then you get 1.67. So that 1.67 is the target for DME3. When you go to the graph, you see that, that's true. If you look at DME3, if you hit this portion here, okay, if you go and then you were to hit this portion here, this very portion, and you have to trace it down, you will see that it's 1.667. And then if you have to trace it to the left, it will be that. I'm just using the graph to demonstrate, but in exam, you're not going to use the graph to demonstrate. Okay. So that is how you calculate the slabs. This is how you calculate this. The target for DME3's input 1. Now, what about input 2? The same values. You take the same values, multiply by the input 2 for DME2, input 2 for DME5, and then you add them. And that one will also give you 1.666. Therefore, the target for DME3 for input 1 is 1.67, for input 2 is 1.67. So that's 1 and 3, which we calculated here. That 1 and 3, which is here. Okay. And the 2 and 1, these ones here. Okay. They are the input. So they are the respective input of DME2 and DME5, who are the role models of this DME3. So how do you calculate, how do you get a target? Now you have seen that truly you get a target by 1, using the theta. Remember that formula. With the actual, subtract the slack from it. Then use the theta again. Sorry, use the lambda, okay, and then the PS. So use the lambda and multiply it by the input x1 or x2 for the PS. And then do the same thing for the other side. If it is output-oriented model, it's the same. Output-oriented is the same. Well, input up, you have to do one at a time. So input up, you have to do input separately, output, and it's the same thing. Now, do you remember that the target for DME1, when we calculated it using that approach, because there was slack for the second one, you have to go and subtract that 0.5 before you move from 2.5 to 2. Remember, if we are to use this thing to calculate, what will it be? Let's go and check the lambdas for DME1. Let's check here. I just want to see whether we have to subtract the slacks or not. What is a lambda here? So look here for DME1, what are the lambdas? You see the first one. You see this one, the lambda here is 0, isn't it? See, whilst this one was 0.333, that one is 0. Then look at the first one. The lambda is what? 1. Okay, so this is how we are going to do it. Remember, the first one is 1. The second one is 0. We're going to calculate the values and see. So this is what we are going to do. This is what we are going to do. I'm going to take the value for, we are going to calculate the target for DME1, X1 for DME1. You have to take this value. You have to take the lambda. This is a lambda. And you're going to multiply that lambda for L2, the DME2. The DME2, its input 1 is what? Is 1. And its input 2 is what? Is 2. But we are interested in input 1 for now. So it's going to be 1, which is a lambda, times 1. Plus, we go and add that of DME5. DME5 will also be 1, the same lambda 1 times, what is the input for DME5? 3. Okay. So, oh, no. So that one is 0. It's not 1. Did you see that? You take it there, the value here. You see that is 0 times, huh? Sorry. So it's going to be 0 times, look at the value, 3. 0 times 3 is what? So 1 times 1 is what? Plus 0. So the target for DMU1 is supposed to be what? 1. And you want to check here, it's really what? 1. Let's check for 2. You will take the same 1, this very value, 1, okay, multiplied by the output. Sorry, the second input. The second input for DMU2 is what? 2. So 1 times 2 plus, you take the 0 multiplied by that of the 5. The that of the 5 is 3. So 0 times 3, 0. So 2 plus 0 is 2. So watch it. So that's why I say both of them, you have to subtract the what? The slack. So if you don't go, oh, no, here you don't subtract the slack. You realize that? Yeah, but that is what I said I wanted to check. So you don't subtract the slack when you are using the lambda, but you subtract the slack when you are using the theta. Put it down. Don't subtract the slacks. Emily, did you know that? Don't subtract the slacks when you are using the lambdas, but subtract the slacks when you are using the theta.
No, Doc. First time I'm hearing of it.
I know. It has to be verified. Because there was a question one time I gave. So that's how you calculate. In short, learn how to calculate the, you know, when I want you to calculate this target, and I want you to use the 2 approach, you know, I will not give you the values here. You know that. Because if I should give you the values, you will just go and look at the values and give me the answers. So normally when I give you these things, I will delete that section here, this section here. I'll delete so that you will calculate the target using the 2 approaches. Okay. It is something you will. You see, most of these things I've been asking that same question. You have to calculate the target. But just that you should remember that when you're using the theta, you subtract the slacks. First, you have to check whether they are slacks. And if they are, you subtract it. If there are no slacks, fine. But when it comes to the lambda, you don't subtract the slack. The lambda is designed to quickly take you to the point that you need to have. Very beautiful point. Right, so that brings us to the end of the entire caboodle.